a real pleasure to be here. I'd like to thank the organizers, Professor Guy Davy, Marcel Filoche, and as well as the PIs of this very nice project, which is the Simon one. So as Marcel said, it's also a pleasure to be in Paris, a place that I lived for 2 years, and I miss it a lot. No? So I come from Universidade Federal do Ceará, which is in the northeast of Brazil, in the very nose of Brazil. And it's a very nice place, nice beaches. The weather is amazingly uniform throughout the year, so you are all welcome to go there. And also, nowadays it's important to say it's the leftist part of the country. So if you have a look in how they distribute the votes, the northeast of Brazil is very reddish, so it's very nice. So we are happy, we are proud of that. So the title of my talk was originally Fluid Flow Localization in Disordered Systems. I put localizations between quotes, between quotations, because it's not really in the context of Anderson localization. But after reading 2 talks from Professor Guillamarck and Professor Tigelen yesterday, when they both quote Philip Anderson, I decided to change my title. My title is going to be something like that. So I think it's much more appropriate. I was really scared about all these mathematicians. My original background is I am a chemical engineer, so you can leave the auditorium now. It's okay. But I've been working with physicists for more than 25 years, so I might consider myself a little bit. I know how to talk a little bit physicist like Svetlana knows now, so I would go forward with this. So, as Marcel said, we've been collaborating a lot. And I had the pleasure to be working with Bernard Sapoval and Marcel Filoche during the 90s, at the end of the 90s, beginning of the 2000. And I was introduced by themselves for these screen effects, as I will tell you now. So, for instance, let's suppose that we have a Laplacian system. So this is an interface. You have Dirichlet boundary conditions here, and you apply a constant concentration, a constant temperature, a constant voltage. And this is, for instance, the counterplot of the temperature or the concentration or the density, whatever you want, inside of the bulk. So you have particles or mass or heat that goes from this place to this place, and as has been nicely shown yesterday from Professor Engenstein, I'm sorry, yes, always difficult for me. This is some sort of, so the system doesn't see very well. So if instead of calculating the temperature, and you calculate the heat flux on the interface, what you see is that, in fact, indeed, the heat flux is only observed by very few spots on the interface itself. So this is a fractal interface, a disordered square curve. And Sapoval and Filoche have been publishing a lot since 1994 on that, 2 physical review letters. So when the chemical engineer arrived, so we decided to publish in chemical engineering science, so that the chemical engineers should know a little bit about that. So I'm not sure if they got interested on that anyway, but they should. And I was introduced at that time, it was almost 20 years ago, no, 15 years ago, sorry. I was introduced to Makarov's theorem. It was my first shocking experience with mathematicians. And Bernard showed me the theorem, published in 1984. The information dimension of the harmonic measure is equal to 1 in 2 dimensions. So for me, it was easy to understand. You have a very regular, very tortuous interface. You have a Laplacian of the concentration here. I like very much mass transport. You have a constant concentration here. And you have Dirichlet boundary conditions at the interface, as I already said. And then Makarov, after 64 pages of derivations, Makarov came to this conclusion here, which, of course, I did not understand very well. Bernard, at that time, I was more a chemical engineer than a physicist. I asked Bernard Sapoval to explain me that. And then he gave me a much better meaning. So the set where the activity takes place has a dimension equal to 1. So the length of the active zone is proportional to the system size. Wow, this was amazing for me. So the active zone is proportional to the system size to a power alpha, and its alpha is not equal to, for instance, it should be equal to 1, whatever the irregularity you have. At that time, I knew already something about fractals. So I could know that you might have dimensions which are different from one in this particular case. So, and then more than that, I decided to think about, for engineers, what is the Makarov theorem? So, and then I took this, Bernard together with me, we did this sketch which was very, very nice. And then, for instance, this is, there is this, so if you start now with a square Koch curve and you go from generation to generation of that, so what you simply say, suppose that you have a catalyst here. And you cover this catalyst with gold. This is a plane interface. So in this particular case, Makarov theorem works, of course, and then you have 100% of activity. So the alive interface acts completely, and it's equal to the active interface. So now if you fold it and go for the first generation of the Koch curve, of course, then you have a ratio of 5 to 3 in this particular case, and then only 60% of the surface now is active. If you keep doing that, you only have 36% of the surface active in the next generation, and so forth, and so on. And this is amazing for engineers. So many catalysts that you use to cover their interface, in many catalysts you use gold or platinum. So in fact, if you do that, and if your catalyst has a surface which is a fractal, it's a waste of time, and a definite waste of time. So engineers don't know that, and this is shocking. I have to tell you this. So, especially for fractals. Then we decided to work on something else. And then this was my first contact with Philoche. This is Professor Philoche. At that time, he was already famous, and then he was a monster of physics. But Philoche is not so ugly as you can see. This is a much nicer guy, very gentle. So we decided to work on fluid flow. This was an idea that we had. So perhaps Makarov theorem has some implications on fluid flow itself. And then we decided to work on that. We managed to publish our physical review letters. And the idea was to make an analogy between the Laplace. So confront Laplace against Stokes, the famous fight, English and French, no? Yes. And then you have, okay, the same system now. I just changed it from voltage, from an electrical current. And what do you have here? If you solve the system, if you do it numerically, or whatever you do for the same type of structure, the same type of interface, you can draw an analogic fluid flow system, which is this one here. Okay? So suppose now that instead of the Laplacian, you have the Stokes flow. So you have it's in fact a tube which has a very, very tortuous interface, which can be a fractal. You have Stokes flow here. So the velocity at the center is more or less and approximately equal to a constant velocity, which is similar to the original one. And then you have the Dirichlet boundary conditions here, non-slip boundary conditions, which are actually, in reality, used in engineering projects. So, but now what is the flux? The flux is simply the stress calculated in parallel to each element of the interface. So you can calculate that. If you solve Stokes equation, 0 Reynolds in this particular case, this is the type of solution that you get. Okay? In this case, in this particular case, for a square Koch curve. So of course, the solution is not different. This is a vectorial equation, as you might know. And you might see that these zones here are not stagnated, as people might think. You generate vortices. So even at 0 Reynolds number, people might have the impression that you don't have vortices, but you indeed have vortices. So if you go and remove these vortices, because now they go deep inside of each structure like that, so if you now remove them so that you can see the other ones and amplify their magnitude, these vortices go on and go on through the deeper reentrances of this interface, generating other vortices which are somehow synchronized. So, but the decay of the vorticity itself, which measures the intensity of this, decays exponentially. So for the sake of the stress, they are not very important at this particular Reynolds number. Anyway, so what did we do? We calculate those stresses that I told you for different systems. The system which is the Laplacian, and the system which is the Stokesian. And what we saw, this is the spectroscopy I, is simply the number of the plaquette, the number of the element of the interface corresponding to each simulation that we did, each numerical. And they are extremely similar. So we saw they were very similar. No? So indeed, what you see is that perhaps there is some analogy between Laplace and Stokes when you use the Makarov theorem with those special boundary conditions. Okay, what? Sorry.
The axis I and V.
I'm sorry?
Could you explain what's on the two axes?
Okay, so this is the flux for the Laplacian one, which is simply the heat flux on the interface, on each element of the interface. I is the elementary unit of the interface. So I'm going through.
Just order the.
Yes. I'm just going through every element of this. This is I equal to 1, I equal to 2, I equal to 3, and so on and so forth.
So it's a normal derivative of harmonic function.
Right, that's on the left. So on the right, what are you measuring on the right? In the top graph?
In the top, I'm measuring the stress.
Still
The
normal
normal
derivative.
derivative, but V is a vector.
No. V is the component of the velocity which is parallel to the interface. That's how you measure the
So it's the
stress.
strength.
This is stress.
Gradient of strength.
Yes, this is called stress in fluid dynamics.
Yeah.
And this is how you define, for instance, the dissipation at this particular point.
So again, V with those two.
So the velocity is
V parallel.
the parallel here means the component parallel to the interface.
Should make a drawing on the board.
Yeah. So
What's the mechanical stress?
I mean,
It's an
V is a
interface.
vector. I just need to know which.
So V is just the component.
It's a normal derivative.
It's a normal
The
derivative.
normal derivative of the
Yeah.
tangential.
Exactly.
Yeah, for mathematics it's a normal derivative.
Okay.
All right.
So what did you do if you plot phi L against phi S? You see that they're indeed linear. So we thought that there would be an analogy between them. It's for the mathematicians to show it's correct or not. I give it for you. Nobody has ever done that. I think it would be interesting to prove somehow, because it's a linear equation, vectorial, but it can be very difficult. I don't
They are
know.
actually just multiples?
I'm sorry?
They are just multiples?
Yes.
Okay.
Yes.
Somehow it's the same equation. No. I
No,
mean, you say proportional.
no. This is vectorial. No? And you have the body force here, which is the pressure. So you have to.
The pressure is implicit.
It's implicity. It's an external force.
Did you try other examples?
Sorry?
Did you try something else?
Yes, we did. Yes, for different system sizes, it's the same.
So if you did it with a small eigenvalue, like Laplacian V is equal to some, a small multiple of V. I'm just wondering whether the plots would look the same. I mean, depending on that parameter.
I didn't do that.
Yeah, I'm just
Maybe.
to make a comparison. I mean, whether just some perturbation of this other equation,
Yeah.
how far it goes from that. I mean, it's probably the same.
Yes, I would say it's the same. No?
Yeah.
Of course, yeah. Here we just
This is
put them together because the order of magnitude. Sorry?
What's the P in this? What's the pressure on this? What's the gradient of
The pressure is not really not important. Here what's important is the Reynolds number. The Reynolds number is very small. So the Reynolds number is the ratio between the inertial and the viscous forces. So the Reynolds number here, you can say it's 0. So inertial effects are not considered. So that's why we can have Stokes equation. I will show you now. We are going gradually from Stokes to laminar, and then at the end of my talk, turbulent. And then if you want to see something which is even more turbulent, and if I have time, I will talk about Brazilian politics. It's true, but I'm sure if not Marcel. Anyway, so now we go for something different, like MonPython. No? So localization in flow through disordered porous media. So in this particular case, we have I have to define a geometry which is completely different from the previous one. So the porous media is percolation-like. So the disorder is binary, so you simply allocate, you have a square. We do it in 2 dimensions. That was back in 1999. We didn't have computer power to do that. So we have a square or a rectangle, and we allocate obstacles, which are also small squares, on this rectangle. And what is between this is the space for the fluid to flow. Okay, so it's a binary disorder, and epsilon here, so the probability to have an obstacle is equal to P, so 1 minus P is what we call the porosity of the porous media. Okay, so the phenomenology here is a little bit more complicated than Stokes, as I was going to tell you. So you have Newtonian fluid. We will also go for that complication later. Isothermal, incompressible, and of course we draw the time derivative of the Navier-Stokes equation. So what do we have here is continuity. You have to conserve mass, and you have Navier-Stokes equation now, which corresponds to momentum conservation. And differently from the previous one, now you have this nonlinear term here, which accounts for the inertial effects on the system. And the Reynolds number, as I defined before, is simply this one here, which accounts for the ratio between the inertial forces and the viscous one. In that particular case, the Reynolds number was equal to 0. Now we're going to change it and see how things localize. So that's what we get when we do the simulations on this. So this is a typical realization of the system. They were small at that particular time. And what we are plotting here are the stream functions. So the stream functions for it's possible to draw them from incompressible two-dimensional flows. And they are basically that. And they can be, physically speaking, analogous to the trajectory of a particle, a tracer particle, which goes from one place to another, driven by the fluid. So if you release a particle here, it will follow this trajectory here. And then we did that for Stokes flow, again, low Reynolds number, and we did that for high Reynolds. High, I have to quote that because it's high, but not high enough for us to have turbulent motion. So we don't talk about turbulent. It's still laminar, but not turbulent. So what you see here is that you have the presence of preferential channels in this particular case. So these preferential channels are something like a more localized type of fluid. So it's possible, and then this is what we saw, a stronger channeling in the case of Stokes flow, which somehow is a little bit counterintuitive. I wouldn't expect that, because you are in a very linear regime, and I would expect this to be less complex than the previous one, which are straight. But as you think a little bit deeply, you will understand that the viscosity itself leads the fluid to consider, let's put it like that if it's possible, distant barriers. So the correlations at low Reynolds numbers due to the viscosity are much higher in low Reynolds numbers. And then that's why you have things like that. So what do? We can calculate some sort of participation. That's what we did at that time. And what we see here is it's a log of the variation of the participation with the log of the Reynolds number. And as you can see here, for low Reynolds number, everything is the same. But as you start having the presence of inertial effects on the fluid flow, the participation starts to increase. So in fact, the fluid flow is more localized at low Reynolds number than at high Reynolds number. Okay. So yes, and why is that? Because of the presence of channel effects. So the fluid tends to follow very special channels. So somehow the fluid optimizes its way through the disordered system. Okay.
So participation, I'm not understanding what's more and what's less.
Okay, I will tell you. I didn't explain yet. Yes.
What?
Okay, I didn't explain.
When it's less, it's more localized.
Do you understand the participation is there?
No? I don't understand the vertical axis.
Oh, yes,
it means more participation.
No, the participation here is defined in this way. So it's the number of elements in the system that you have available for fluid flow, and you have the summation of the key y to the square minus 1, which is the inverse of this one, and key y is simply the partition of energy. So you have the energy, the kinetic energy of each element of the system, and you divide it by the sum of the entire energy of the system. So it's the fraction of energy which corresponds to the element.
Right, so,
okay.
So if there's higher concentration, as if the QIs are
yes.
larger, few of them are larger,
yes.
you have, does this number get higher or lower? Because of that reciprocal.
Yes, exactly. So if P is very small, it means that you have some sort of everything. If P is very small, close to everything is concentrated in a single element. Okay, and if P is very large, let's say infinite, it means of the size of the order of the system size, it's completely spread out. You have equal partition of flow, of energy in the system. Okay, so this is what's happening here. So we went there to non-Newtonian fluid flows 3. We did the same thing later on because we have more computational power in 3D. We observed more the same thing, and we published our paper. I will not have time to show it here. Then we go for something else. Now I wanted to go to turbulence. So So this is more recent. But before going to turbulence, I wanted to understand it a little bit, and we decided to play with a toy model, a baby model, as I heard yesterday from Zeppelin. So, and then we decided to work with packings. We went to a classical system instead of working with the fluid dynamic systems. And then we decided to use some sort of Apollonian packings. And as you might know, they represent the extreme case of they are perfect filling or complete filling packings. And it's possible to prove that they have power law distribution of sizes when you do that. And what you have is a peculiarity, and Mandelbrot called it a self-inverse fractal, in the sense that what is inside between the beads is the fractal, not the beads themselves, not the set of beads themselves. So, so you start the generation 0 of the Apollonian. This is the generation 0. What do you do now? They touch each other in a single point. What do you do now? You fill the interstices of this packing with other circles. You keep doing that. In order to do that, you can use conformal mapping techniques. It's nice to do that. I will not have time to show it. If you want, I can show you later. So you keep doing that, and so on, and so forth, to the point you have a space filling object. So, as I said to you, the porosity of this object, it is what is fractal, not the object itself, not the solid part. Okay, the solid part is space filling in the limit of an infinite number of particles. Okay, so the fractal dimension, people have tried to work and determine the fractal dimension in this particular case. For the two-dimensional Apollonian packing, the fractal dimension of the dust, which is between the particles, is more or less 1.3. And numerically speaking, this has been improved. This is a rigorous bond found by Boyd in 1973. And Hans, Hermann, and Manna found a much better numerically value for the fractal dimension of the dust. So this is the three-dimensional Apollonian packing. You can also work on that. But now the Apollonian packings have, now I want to put some dynamics of that. So as I told you, this is a toy model for, the fluid dynamics systems that I want to understand. So it's funny because now I want to turn I want to transform those beads in rotors. I want to twist them to make them turn. So if you do that to the Apollonian, they are not very nice, because if you turn these in this way, and now, of course, before doing that, you have to allow the system to have some friction between the touching points. So there is friction between the touching points. So if you turn this one induces a movement on this one in this way, and because of that, this one doesn't know where to go, so it's a frustrated. So is there a way to generate a non-frustrated Apollonian packing? Yes, there is. And this has been proposed in 1990 by Hermann, Mantica, and Bessis. They also use the inverse method. So instead of starting with 3 touching disks, they put a small disk between them already, and didn't allow the 3 disks to touch themselves. So when you do that and you use exactly the same procedure, but as we will see now, you end up with things like that. So it's not frustrated anymore. Okay? So, and then you keep doing that. Okay, and that, and so on, and so forth. Okay?
So the small ones turn very fast.
Very fast, yes.
Is it always true that every disk of the same size turns in the same direction?
Because of the symmetry here, definitely, yes. Okay, but I go back here just to show you that in order to have this, and for the system not to be frustrated, you need 4-fold loops. So if you leave this place, and you want to come back to this, you have to accomplish a trajectory of 3 steps from outside to inside. And also it's bichromatic in the sense that you have only, of course, because it's 2-dimensional, only 2 directions of rotation. And okay, so shall it be a toy model for turbulence? Because I have vortices. The question is, maybe yes. So I took these photographs from this paper of Journal of Fluid Mechanics, 1995. It's a surface quasi-geostrophic turbulence. Don't ask me exactly what is this quasi-geostrophic. I don't know, but it looks like that. This is a simulation. And you see vortices. Of course, they don't have a shape of perfect circular objects, but they turn and they are non-frustrated. Okay, they have to be, because otherwise they would not move. Of course, you have a source of energy in the system, but anyway, we will discuss about that later. So we published our paper on this, And can you see it turning? Can you? So I wanted to make the cover of PRL. I didn't manage. No, I will explain. And this is the adaptation of a Japanese guy who's an expert in optical illusion, Kitaoshi Yakioki. So he did that, and then he did that for systems of particles of the same size. I can explain the mechanism of the cognitive mechanism for that later during the coffee. You want to know? I can explain you now. I don't have time now. But I would like only to say that we put that in the paper, and I received many complaints because people could not read the paper while watching this. So one of the guys wrote me very, very seriously, "Why did you do this? I cannot read it properly." So it's really annoying, you know? Anyway, so we can put some physics on the top of that to see how does it work. And I want to know some localized features of that. So the basic thing here, you have dynamics, and you have to allow friction between the contacts. So at the end, at the steady state, you can immediately induce in fear that there will be a suppression of sliding friction because they will all turn at the same tangential velocity. Okay, so as I wrote here, sliding friction is suppressed if you ensure that loops of touching disks have, of course, the recipe of the bearing state. I call those elements bearings, okay? At the steady state, as I said, the tangential velocity is the same. You can write down the rotational equation of movement, Newton's equations for the rotational motion of each rotor, okay? So I here is the rotational inertia. It replaces the mass in the original equation of Newton. Radius of the rotor E, and Fji is the force of the rotor J on the surface of rotor E, which accounts for the sliding friction between the touching points of this. What do we do here to simplify things is to assume that this sliding friction is a linear force which is proportional to the difference of to the relative velocity between the two touching disks. Okay? At the steady state, when time goes to infinity, these velocities will reach both the same tangential velocity, and there will be, as I said before, suppression of the sliding friction. So the system will reach a non-dissipative state, which we call bearing state. Okay. Now we do the following. So we need some additional degree of freedom to see how does it work. So what we did here was to introduce some sort of constitutive relation between mass and radius. So now suppose that we are not necessarily working with particles which are made of the same material. So particles which have different density, they are made of different materials, for instance, or they have a hole between them. Okay, so you can do that using a very simple form. The one we choose here, this is ad hoc, was that the mass would be proportional to the radius to the power alpha, which means that the density of each particle is proportional to 2 minus alpha. Okay. Okay, so the density is not constant for different particles. That's all. So you can have a very heterogeneous system. And then, of course, because of that, the rotational inertia, we will have to account for this constitutive relation, which is not homogeneous anymore. So when you do that, you can calculate, you can solve the system. You end up with those equations as a system of linear differential equations. And you can solve that analytically. Not analytically exactly, but numerically, because it can be very large as you want. And at the end, you can calculate the eigenvalues, the entire solution, as well as the eigenfunctions, and then end up calculating. We did a lot of things to show the synchronicity here, but I will not talk about that. All I want to talk is how the energy dissipates in this system. So you can calculate the relative dissipations of disk I in the eigenmode K. Okay, so this is how we do that. So if you sum over all eigenmodes, you will have how much that dissipate before it reaches the steady state. Okay, or how is it dissipated? Okay.
So I'm not sure. What is an eigenmode? So where do you have an eigenmode?
Okay, you have to solve this. I went too fast on this one. You have to solve this equation for each element of the system. So they are coupled by the friction.
So I thought that if you make one big turn, you force immediately the rotation of all others.
It will take some time because they are all you start with zero velocity.
Ah, okay. Okay.
So then you have to dissipate before it reaches a non-dissipative state.
Okay.
So there is a dynamical. So you can solve this dynamic and calculate how much You dissipate before till it reaches the steady state. Okay.
They slide along the contacts.
I'm sorry?
They're sliding along the contacts.
Yes, 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 yes. They're sliding along the according to this empirical.
It's a linear friction rule.
Yes, yes. According to this, it is an empirical law.
Right.
The simpler one I could do so that the system would stay linear and I could solve it easy.
Harder to find eigenvalues.
Yes, 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 yes. Yes. Worse than that cannot be. You know? Anyway, so this is what you get, no? So I thought that, okay, as I said to you, alpha equal to 2 would mean that all the particles have the same density. They are made of the same material, but this is not necessarily the best one, because you see that this is the dissipation for each disk of radius r, okay, for different values of alpha. So as you can see, alpha equal to 2, this is highly heterogeneous, because we have a log-log plot here, okay? But when you have alpha equal to 1, practically all disks dissipate at the same rate. So it's not trivial. We can show that numerically. We don't have a proof for that. But this is more or less what happens. So you have for alpha equal to 1, this type of dissipation. This is log. Of course, there are fluctuations. Log attenuates every difference that you might have here. It's a trick that physicists use a lot anyway, but alpha equal to 0, alpha equal to 2, which is the case of the entirely homogeneous material. That's what you have. So this is a nice toy model to show that depending on the constitutive function that you elect, you have a system which is entirely delocalized in a way. We could have calculated the localization here, the participation function here. We didn't do, unfortunately. I thought about that a couple of weeks ago before coming to this conference. And this is highly heterogeneous. Okay, and this is also highly heterogeneous. So the system, you can optimize, according to a given constitutive equation, the system to make it as less heterogeneous as possible, depending on the material. So, of course, this is a strange construction. So then we went to turbulence. How much is that, Marcel? I'm worried about the politics. A lot of time, no? 32 minutes, according. Okay, so now we go to the next level of the fluid dynamics, which is the most complicated one, and mathematicians played a very, very, very important, modern mathematics played a very, very important role here. So we go first to Newtonian turbulence. So what I would like, many of you know already what's turbulence, but I'd like to show this slide. So what are turbulent flows? Turbulent flows, so they have this cascade of vortices, so they have vortices, they have different sizes. And through these vortices, it's known the energy is passed from very large scales to very small scales till it goes to the tiniest scale, which is the dissipation takes place through the viscous mechanism, okay, through viscosity. So this is a picture made by Richard Lewis, and this is exactly, you have an inertial range of energy cascade, the cascades go on and so forth, till it goes to the Kolmogorov scale, and energy dissipation takes place, okay? So when you do that, it's possible to see that there is a power law. If you plot the energy spectrum, now you go to the Fourier spectrum of that, you see that there is in order to show that this cascade is scale invariant, you can observe that experimentally, that with a slope which is close to -5/3. So this is where the energy is input. This is inertial subrange. So we are playing here with the wave number. So we're increasing the wave number, and this is the spectrum of energy. So you have energy input here, and you have viscous dissipation. In what we call the inertial subrange, you observe a power law. And this power law has a very nice exponent. Okay? So let's go to do some experiments. Quotations, numerical simulations. Dirty numerical simulations, okay? So now this paper has been submitted. We have a lot of trouble because this field, apparently, fluid mechanicists don't like people from outside to publish in their field. No, I'm not sure this is a common thing in other fields, but we've been trying very hard to publish this paper. So I'm not going to the details, but what we did was to do simulations in a cubic box. We ended up with a fluid which has an additional degree of freedom as before. So the mathematical formulation is very similar to the previus one, but it's not Navier-Stokes anymore. Of course, continuity is always the same. You have to conserve mass in your system. The momentum conservation equation has to change now because I want to add another degree of freedom, which is instead of being the density in the particular case of the bearings, now is the viscosity. So I want to see how this degree of freedom will affect the partition of energy in the system. And because of that, you have to calculate the deviatoric stress tensor, which is in the case of the Newtonian fluid, B of the strain would be a constant. This is so-called the Newtonian fluid. The stress is proportional to the strain, and the constant of proportionality is viscosity. Okay? Here, the viscosity itself is a function of the strain, which makes this problem non-linear in the viscous term of the previous Navier-Stokes equation. So it's another non-linearity which has been added on the top of the inertial non-linearity. But this inertial non-linearity is the one which is important for turbulence. Okay? So the strain rate tensor is calculated like that. This is how you calculate strain. So this is where gamma, the strain rate is the second principal invariant of this. Okay.
Can you just say what those things are? So the bottom line, the dot. Why is there a dot above that?
Which one?
Above the gamma.
Because this is some sort of the derivative of the strain. It's a rate. It's a dot.
But you define it without differentiating. So afterwards there's a square root of something.
This is a common thing because this is a strain rate.
But that gamma dot is equal to this thing where I don't
Yes.
have to differentiate.
It is, yes.
Yeah, so it's just equal, so it
Yes.
could be any symbol.
It could be any
there.
symbol, yes,
But
yes.
So
This is
there
a
an
jargon.
interpretation of the gamma dot is the derivative of what?
Gamma dot is called the strain rate. It's how the stress affects the dilatation of
So
the
but
fluid.
why isn't it a tensor rather than a scale?
No, what is a tensor is a strain rate tensor.
Yeah.
This is the strain rate.
So then why isn't the derivative of the strain? I mean, in other words, which direction? Why are you picking one scalar number?
It's not, it's components of the gamma dot.
Because I need to refer this to mu somehow.
Where would d that is just the L2 normal figure.
I don't understand very well the question. So.
It's the Hilbert-Schmidt norm. Square root.
Yes.
So the Hilbert-Schmidt norm, okay, and so it is a scalar.
It is a scalar, yes, definitely, yes.
And
So it's a double dot
it's
between the
just
strain.
It's just the total, okay,
Yes.
the total strain or something like
Yes,
that.
yes, yes. And then that's what, because
And then mu is a function,
Mu-
mu is a factor.
mu is in the Newtonian case, mu is a constant. It's not a function of gamma dot. And in this particular case, tu is proportional to E.
T is proportional to
In
E.
the Newtonian case. So mu is not a function of gamma anymore. Mu is a constant. This is called the Newtonian fluid.
So those parentheses you could eliminate and it would still be the
Exactly.
correct equation.
Yes.
Okay.
So this is a
All right.
generalization of the Navier-Stokes
It's just
equation.
your notation. Mu of, it looks like it's mu is a function.
Oh, I'm sorry, yes.
Of gamma dot.
It is. Mu is a function of gamma dot in the non-Newtonian version of the momentum conservation equation, which is non-Newtonian. In the Newtonian one, mu is a constant, so it's not a function of the strain. You are adding this. This is the
So it's
additional.
the function. So you haven't told us what that function is then. What mu of gamma.
No, not yet. It's the next slide. I'm sorry.
It is a
It is the next slide.
Can I ask a beginner question?
Yeah.
This word invariant makes me think that something is. What's an invariant under? Sorry, this is a very basic question.
So I don't know.
Oh, it's just. It's
Why is it invariant? It's a trace. No, it's a trace.
Oh, well, we hear it a lot.
Yes, it's a trace. Yeah, it's a good question. I'm not sure.
Invariant is like invariant and covariant. Doesn't mean invariant.
Maybe it's because it's the trace of the tensor, no? Maybe this is.
What are the three symmetric functions of the eigenvalue?
Yeah.
Okay.
No, I'm okay. Sorry, now I don't understand.
I never expect people to make questions. Very nice. Thank you.
Mathematicians really would like to know what the symbols mean.
Of course. I'm sorry. I'm deeply sorry. I'm deeply sorry.
It's extremely similar.
I know.
to what we
Very
already
good.
know.
Fantastic thing. Sorry. I'm sorry. Anyway, so this is your question now, okay? So how mu is a function of gamma dot? So this is what we call cross-power law fluids. In the case of cross-power law fluids, you have a Newtonian one, which is in the case n is equal to 1. So you have this exponent here, which parameterizes our functionality. And if n is equal to 1, you go back to the Newtonian case, of course, where mu is a constant. If n is larger than 1, you have what we call a shear-thickening fluid, which is, let me see what this ketchup is a very nice shear-thickening one, because it looks like a solid before you allow it to be strained or stressed. No, ketchup is shear-thickening. Shear-thinning, sorry, shear-thinning. And then yogurt, shear-thinning as well. Thank you, Marcel, yes. And when n is more than 1, it's shear-thinning, which is blood. Blood is shear-thinning, okay? So we decided to use that. That was an arbitrary, but it's also kind of general type of description for the rheology of the fluid, as we call it. So now we have something else, which is somehow analogous to what we call the thermodynamic equilibrium in fluid dynamics for turbulence. So it's a central assumption of turbulence, and it is because of that Kolmogorov could develop his approximative theory of 441. Is that the fluid is homogeneous and locally isotropic. So you have to allow for that, otherwise you cannot go anywhere in his theory. The so-called fully developed turbulence. So we are in a fully developed turbulence. It's still non-steady state, but it's still transient. But you have so there are many ways to do that. You can do that. Usually people do that in the Fourier space and trace it back to this physical space. What we did here is a very simple but very recent technique, which you simply say that you have a linear forcing term, and you add this linear forcing term in the previous equation. I didn't show it to you. It's here. Okay. So what you are doing here is that you are always adapting the local velocity of your fluid to the global average velocity of the system. This is like God doing something at every point of the system. So it's something similar to the Maxwell demon or something like that. And you do that using some sort of turnover time scale so that it will reach the fully developed turbulence according to some characteristic time. It works. It works, and how do we know it works? Because it produces the rigorous result of Kolmogorov, which I will show you here. Okay. Okay. So these are technical, dirty details of the numerical simulations. We use this code here. It's not worse to start from scratch, writing codes to solve it, because you have a lot of work trying to use those codes already. I can tell you it's a very, very precise and refined technique. We could not go for very large system size, 256 Q. Why didn't we go that? Because we need to vary a lot the exponent of the constitutive relation of the rheology. I have but now you have to do something what Marcel and Svetlana is doing. So you have to try to understand the confinement of the fluid in terms of some particular value, as you did in the localization. And what people did here is how to define a vortex in this system. So there is a paper which did that, and this definition has been used a lot by fluid dynamicists. So what they did is they calculate the second eigenvalue of the tensor E squared Q squared, where now Q squared corresponds to the vorticity of the fluid, the local one in 3D. Okay, so as you remember, EU corresponds to strain, to the stress, and Q is now the vorticity. Somehow, so you want to understand the vortex as a place which accumulates vorticity and avoids stress. Okay, because it's a vortex. And a vortex is defined as a connected region in space with at least two negative, because this matrix is symmetric, you can define these vortices. And lambda 2 has to be smaller than 0 to define the boundary of the element. I will not go into the details of that. There is a very nice paper by Young and Hussein trying to define that. And so the vortices are then identified in using this technique. If lambda 2, you can generate some threshold. The original one is lambda 2 equal to 0, but if you use that, you see a lot of finite size scaling. It has to be slightly smaller than lambda 2 equal to 0 for the system not to cover a single vortex completely if the system is small. So this is what you see after simulation and fully developed turbulence has been achieved. And as you can see here, using this is for a shear thickening fluid, using lambda 2 equal to minus 10 to the 5. As you can see here, on this cross section of our system, as you can see, the system, the vortex definition captures the intensity of the vertical motion and avoids the stress. So the vortexes are indeed turning, but turning not nice vortex as I shown you in the case of the fractal tube. In 2 dimensions it's very easy to identify because they are simply like that. Here no, they have strange shapes, very strange shapes. Okay, so what did we do now was, okay, now we have vortexes, we could quantify them, and now we can calculate the distribution of vortex sizes in this system. Okay, to see how robust is the turbulence structure to the rheological property that we are imposing. The rheological property, I mean the variation of the viscosity with the strain rate. And apparently, it's not sensitive at all. I mean, of course, these are log plots, but as you change the index of the rheology, this is the Newtonian one, this is the shear-thinning one, these are the shear-thickening one, you see that the vortex distributions are more or less the same. So the structure of the fluid flow is what we call the coherent structure of the fluid flow are preserved, even if you change dramatically the rheological properties of the fluid. This was not exceptionally expected. So this guy Townsend in 1980 already expected that, and he wrote that in his famous textbook. He didn't do simulations to understand intuitively that if you change the rheology, the cascade of Richard Lewis would be maintained. Doesn't matter what you do, it has to be like that, otherwise it will not work. So we observed, people knew that, but people didn't do calculations as we did. So, but what is the mechanism behind that? So the mechanism behind that is energy dissipation. So where is the energy being dissipated in this system? So of course there is only one mechanism for energy dissipation, which is the viscous dissipation in a cell. So and it can be calculated like that. And as you can see here, the dissipated energy is typically smaller inside the vortices than outside them, of course. And regardless of the rheology, this is a typical case for n equal to 1.5. So as you can see here, this is the boundary in that very same cross section. As you can see here, inside the boundary of the box, you don't have dissipation or very little, and outside where it is where dissipation takes place. So when you do that for different values of lambda 2, you observe exactly the same. For different values of the exponents of the rheology, as you can see, for low values of lambda 2, which is inside of the vortices, it dissipates much less than outside the vortices, generally speaking. But of course, there is a difference when you go from one exponent to the other. So there is a mechanism to maintain the structure, the coherent structures of the vortices invariant in terms of their distribution, statistically speaking. Okay, so, and this is interesting. So now if you calculate the ratio between the total energy, which is dissipated outside and inside the vortices, over the entire box, that's what you observe. So here, so sorry, go on.
Maybe I missed something, but
you did.
I saw that in the Kolmogorov cascade, the energy was always dissipated within the smaller vortices. And here you are telling us that the energy is dissipated outside the vortices. Or maybe I'm
this is not.
I mean, the classical view of.
But this is not this is inside of every vortex. Lambda 2 defines the boundary of each vortex, every box. I'm not stratifying it in terms of the difference. I'm not saying that it's each vortex will have a scale of Kolmogorov. Okay. Now I'm just. Do you understand that?
No, maybe you can.
The scale of the Kolmogorov scale is much smaller than the scale of the smaller vortex. It has to be. It's microscopic. The vortex is just something for us to know how the structure of the system at the mesoscale is being built up. Okay, so what we see here is that, okay, relatively to a Newtonian fluid, because here now we divided the dissipation outside and inside the vortices by the dissipation inside, the ratio of the dissipation by the ratio of the dissipation of the Newtonian one. And as you can see here, this is what happens. So relatively to Newtonian fluids, shear-thinning fluids, they somehow adjust to increase their dissipation inside the vortices, while it is the exactly opposite for shear-thickening one. So in this way, we can observe that non-Newtonian fluids, they somehow self-organize in terms of dissipation to keep the distribution of coherent structures invariant. So this is, and now, more interesting is the localization. So as you increase the index of the rheological exponent, of the rheological function, you see that shear-thickening fluids are much more localized than shear-thinning ones. It's exactly the same things in terms of energy. Okay, so the localization goes on and over as you go from shear-thinning to shear-thickening. So it's somehow there is some localization in turbulence that needs to be better understood. Okay, my goodness. Ooh. Oh, this is a bug a German friend of mine put in my computer since 2014.
You have 7 of them?
No, I don't know. I forgot to say that I'm also a compulsive liar. So that was traumatic for Brazilians, you know. So I would like to talk about Kolmogorov, but what we did is this is a challenge nowadays for turbulence people to understand how the Kolmogorov 5-force law works. This is not a challenge anymore. This is a solved problem that he did. It's an analytical and rigorous result from Navier-Stokes equation itself. But the K41 theory is not. It's still object of study, and there are what people call anomalous scaling from that, which are the deviations of this theory. We found, I will go very quickly on that, we found that it depends on the rheology of the fluid. The anomalous scaling is non-universal. But this is something that I don't want to go. And then I would like to talk about politics. It's just, I hope because it's a duty of a Brazilian to talk what's going on in Brazil now. I will spend my last 5 minutes of your patience talking about something which I think is somehow interesting. So the role of correlations in political crisis. So we talk about correlations everywhere. But here is special now. And I want to talk about this because I want you to understand what happened in terms of the Brazilian congressman for the impeachment to take place. Okay? There was an impeachment. So how the Brazilian politicians vote. We now understand how do we vote. No? But we don't understand how do they vote. So is it possible that a physicist or a mathematician can try to understand that? Yes, okay. This data is available from the National Congress. So we have 513 federal deputies, and we could compute this large number of projects that have been voted during 2007 and 2015. And what kind of technique did we use? So the technique is the following. How do we quantify those to generate correlations between each congressman, okay? So, of course, you have to quantify it, but I can tell you it's possible to show that whatever you do in terms of that will not change the result I'm going to show you. So, there is a project. You have two representatives, 2 federal deputies, and they can vote no, for that you attribute a number -3. They can vote yes, for that you attribute number 2, and something in between, which are more close to yes than no. For instance, they try to obstruct. They are not there for some reason. They use the Article 17, which shows that they have some conflict of interest, and they simply do not want to vote, but they are present. So this is very close to a yes, somehow. somehow. No? So
So how many of them were things that succeeded versus defeated from, that is, how many of those bills of 1,355, did half of them succeed, or are these only the ones that
no, these are the federal deputies. No?
of the projects?
Oh, this I don't. This is not very relevant for what I'm going to show you here.
So some of them
succeeded, some of them not. Yes,
okay.
but now you can now go. This is some sort of time series where in the x axis you have the project, the bill, and here you have the vote of that particular candidate. Candidate A voted like that. Candidate B voted like that. So these are two time series, and if you cross-correlated them, you can calculate the covariance of this. Okay? So now you can construct a network, which is called a network. No? So candidate A vote like that. Because they are very similar, they will have a strong correlation. And then this is blue, very large correlation. Positive one, because they are similar. Okay, you go on. You now compare candidate A with candidate C. You see that. Similar to. Of course, I did it in purpose. It's a small sample of that. I didn't put all the projects here. You do, for transitivity, you might think that if candidate A voted like candidate B, and candidate A voted like candidate C, it's very, very likely that candidate C will vote similarly to candidate B. Which happened here, in fact. I wanted to show that. And then now you go to the other side of the system. So they are very different from the previous one, but these two voted similarly. Okay, so you keep doing that, and so on and so forth. Now you have to compare B and C. What you can see now, they are very different. So if they are very different, the correlation will be very negative. And then you see some red spot here. So you keep doing that for all the comparisons between pairs of candidates, and you have this fully connected graph, which is like that, separating two different sets of candidates, which must most likely belong to different parties or have different ideologies or things like that. Okay? So if you do that for the entire number of projects and the entire number of candidates, that's what you have. Okay? Complete graph. No? It's very complicated. You can see that this is a special software that we use to separate them, and see there are, of course, two groups. But you can use a little bit more sophisticated techniques. I will not go into the details. But before doing that, you can now exclude the geometry, the topology of this complex network, and simply show what is the distribution of correlations that you have in your system, without considering which pairs of candidates are related to. So when you do that, and you did that for 2007, the first year of the second mandate of Lula, okay, as you might know very well, he's in jail now. Poor guy, you know? So as you can see, there's a typical bimodal type of curve here. So this stands for the positive correlations, and this stands for the negative correlations. So which seems that, okay, there are this is the first year of the second mandate, so the elections just happened. Okay, so it's highly polarized. So there is a group of candidates voting. And then the negative ones, we separate these two groups, that's my conjecture. So if you put the matrix of correlation, so where this is one candidate, this is another candidate, and the color corresponds to the correlation between them two in a random way, alphabetical order, for instance. You will not see anything, but then there are techniques, as I told you. For instance, you can calculate the minimum spanning tree and do it in a hierarchical way according to the strength of the correlations. You can see things like that. And now, if you use the minimum spanning tree on the top of the matrix correlation, ordering it according to the way each site appeared in the minimum spanning tree, you see now that there are two groups here, voting similarly and voting similarly, and between them there are highly negative anti-correlations. Okay, now we go to the second mandate of Lula. I repeat the same distribution of correlations here, and now we go further, year by year. 2008. 2009, 2010. So apparently they are forming a single group. No? So they somehow forgot what they promised to the electors. No? Something is going on here, and this seems to be an evolution to consensus. So they are far away from the electors, from the people, the voters. No? So this is amazing. But this is okay. So now it's finished. The second mandate of Lula. Dilma decade, no? First mandate of Dilma. As you can see here, so because they went back to the streets, to the television. They had to listen to the voters. They made promises, and they somehow believe that they will maintain their promises in the first year. So you still see a bimodal type of evolution here, but it very quickly, in her case, it didn't need 2 years to do that. It went up to a monomodal type of distribution. This is amazing, you know? So, and it kept monomodal till the end. So, and this is the second mandate of Dilma, and it already started. Well, of course, there are some negative correlations here, but you don't see the bimodal anyway. And this is a very strong sign that there would be impeachment. Okay, so I would like to show you that because there might be a way, there are things going on here that we should try to understand. And with that, I finish. This is my soccer team. It's in the 3rd division, and but I still have to support it. So thank you very much for it.
Thank you for this very fascinating course of statistical physics. Okay, so the talk is open for the questions.
Yes.
For the 3D simulation on the cube, did you have just an inflow and outflow, and then the other 4 sides are no slip conditions, or what were the?
So periodical boundary conditions everywhere. Yes.
Can you talk a little bit about the energy in the rotating disks model, the Laplacian impact?
Yes.
So maybe you start by rotating one of the big disks, and then in the end, it seems like all the energy will go to like most of the energy in the system will live in the smaller disks after you hit equilibrium.
Yeah.
So did you try doing this with more and more disks and really see the sort of energy, the total energy of the system almost?
If you say finite state scaling, you know, we didn't do that.
Okay.
We went to the larger system side. Something to be done.
That's cool.
Exactly.
Just a quick comment. I know that Stokes is sort of a toy model for you, but just to sort of provoke communication. At some point when we were doing Laplacian in 10 years, Laplacian was, it's a known fact in the easy computation that the stream function is biharmonic for Stokes.
Yeah.
So we actually looked at the gradient, which respectively gives a solution, and there were quite interesting effects. And we were not looking at the disorder geometry back then, sort of geometries like those Patrick has shown, and how the flow separates and so on. So it might be worthwhile at least to play with it as a toy model to see how geometry affects the flow from that point of view. And I'm saying that to some extent we have tools for that, in particular the landscape thing and so on. So we didn't go very far. We sort of looked at the gradient to see if it's a reasonable, you know, what could happen in the pool of water, and it's kind of reasonable, but it doesn't prevent any further.
This was my hope when I met Makarov in a conference in California. So I met him there, and I was very excited about this result. You know? You see, then he was having, it was a coffee break, and I showed him these results. And then he looked at me, and what do you think? He looked at me, look, I need a coffee. He didn't talk anymore, so I was very shocked. Maybe it's, didn't care so much. Thank you very much, I didn't care, so I'm so happy.
Any other questions? So I have one about the eigenfunctions, the eigenmodes also, the rotating base diagonal. So do you have any, what's characterizing the localization, strong localization is the decay, the long range decay. So did you measure anything?
We did. This is exactly, but now I lost it, no? Okay. Sorry, Marcel. Oh, it's here. Oh yes. So, oops. This is bad news. Huh? You have to edit this. By the way, I didn't say anything about Brazilian politics. I have to find a place for me to work here. So this is what we did. It's called the synchronizability index. This was in fact the most important part of the paper.
Okay.
And how the dynamics of the system evolves.
Okay.
And how the system synchronizes before it reaches the Beering state. So one of the measures of that is simply the largest to the smallest eigenvalue. The ratio between them two somehow measures how do they couple, how quickly do they couple. And as you can see here, for alpha equal to 1, you have a minimum in this index. So for different system sizes, as you see. Exactly. So there is a balance between the contact points, and the size of the system. So inertia versus friction. Inertia versus. So in fact, one of the possibilities, instead of using different material densities, is to have systems which have holes inside. Alpha equal to 1 means that. So probably you do like that, and the system immediately will go back to the Beering state, as you more or less asked. And then we did some analysis of system size as well.
Okay, thank you. No other questions?
Thank you very much.
Thanks.